Alright, so let's work on with this integral. So we have the integral of 1 over the fourth root of 1 plus x from the bounds of 0 to infinity dx. Now, this particular integral over here, this definite integral is what is defined as an improper integral, where you have a bound where your function is not defined. In that case, it's infinity. Um, our function may be convergent or divergent, where if it is convergent, it is converging to a constant, or it is divergent, where it is either where the integral either is positive, plus or minus infinity, or does not exist. So let's go ahead and solve this question, um, and then we'll go through it together. So we want to compute this particular limit. So we need to keep in mind of two things. Yeah, let me take red. So first of all, I need to take care of the integral. Obviously, I'm gonna have to integrate this and bounds. So let's assume I plug in 0 into this function. Well, if I plug in 0 into x, that will be the fourth root of 1, which is 1. So my function is defined at 0. But if I plug in infinity, that's when things get a little messed up. And this particular integral within the improper integral is what people, not people, what is referred to as type 1. So this is type 1, where you're computing a limit when one of the bounds is, one or more bounds are at infinity, where our upper bound is at infinity. Therefore, we are dealing with a type 1 improper integral. So a type 1 improper proper integral. Apologies for the handwriting. All right, so let's go ahead and see how we're going to deal with this. Now, before integrating, we first need to define how we're going to approach this. Now, we know that there is going to be a limit. Of course, if our function is convergent, it has to reach a particular limit, which is a constant. So we can find that by taking the limit of the whole integral. And one way to do this is back to those red the stuff that I've underlined with red, is our function is defined at 0, but not at infinity. We don't know if it's convergent or divergent. Therefore, we take the limit as t approaches positive infinity of the integral, and I just substituted infinity with t, from 0 to t of 1 over the fourth root of 1 plus x. There we go, of dx. Now I can rewrite this as the integral. The integral. What's wrong with me? From 0 to t of 1 plus x negative 1 over 4. Now, obviously, basically integrate this, so the integral would of 1 plus x to the power of 1 minus 4, 1 over 4 minus, would simply be that would be 3 over 4. So 1 over 3 over 4, and then that would be 1 plus x. So basically, you're integrating as normal. There's nothing different about it. And you just add plus 1 here, so that should be 3 over 4. So if we compute that, that should be a 4 over 3. Just bring that guy to the top. And that should be 1 plus x to the power of 3 over 4. And then because we have a definite integral here, it would be from t to 0. So computing this, it would be 4 over 3, 4 over 3, 4 over 3 of 1 plus t 3 over 4 minus 4 over 3 plus 0, 3 over 4, which would simply be equal to 4 over 3, 1 plus t of 3 over 4 minus 4 over 3. So I do need space, so I'll just write that over here. 4 over 3, 1 plus t 4 minus 4 over 3. So I'm gonna go ahead and get rid of this so I can get some space. Alright, so once I've computed the limit, I'm gonna go ahead and find the limit as t approaches positive infinity of 4 over 3, 1 plus t 3 over 4 minus 4 over 3. And if I plug in infinity here, so plug positive infinity into t, this whole guy will be, well, this would be infinity times a constant, this will be infinity, positive infinity, and this is just a constant, and positive infinity minus a constant is still infinity, therefore the whole thing is infinity. Actually, I'll say positive infinity. Therefore, by the way, this simple means therefore, um, the integral from 0 to infinity of the function 1 over 4 through 1 plus x is convergent to is divergent, sorry, is divergent to is divergent. That's it. Yeah, my bad. So let me get to this part right here, because you're gonna ask me, why did we say that the function is divergent? Now, because we computed the limit as t approaches positive infinity, we obtained that the limit of the integral of the improper integral would be to positive infinity. Now, if the limit of t approaches positive infinity, it can go two different ways. If it's a constant, it's convergent, or let's call it k, convergent. If it's plus or minus infinity, or it does not exist, then it is divergent. So therefore, because we computed the limit and we got plus infinity over here, we can deduce that the improper integral is divergent. Therefore, it goes all the way to positive infinity. And we'll work on another example. Should be a very easy example. All right. So okay, this one here. So let me write it down. So we have the integral of sine squared x over root of x from 0 to pi dx. Now, you're going to ask me, Noor, we have the boundaries is from 0 to pi. So can't we just compute it? Well, no. Unlike the previous example where we had the integral from 0 to infinity, we have the boundaries is from 0 to pi here. But we do have an issue, and I did raise that in the previous question, where we need to focus on two things. This function over here and the boundaries. Now if I plug in pi in this function here, it's defined. But if I plug in 0, anything divided by 0 is not defined. Therefore, in this particular example, which I'll refer to as type 2, is determining the definite integral when we have a boundary that is not defined. So that's what makes it an improper integral, right? But now we get into another type of problem. Nor, we have sine squared x over the root of x. Now I have to integrate. It's going to take a long time. It's very difficult to compute it. Now you might be smart and you know how to integrate this, and then you can determine whether it's convergent or divergent. I will help you compute this without having to integrate sine squared x over the root of x, using something known as the comparison theorem, which I'll just say as a comparison theorem test. I'll just CTT. The comparison theorem test clearly states that if you have a function of fx that is less than or equal to g of x, if this were to be convergent, so if f of x were to be convergent, g of x would be convergent. If it were divergent, then my guy here, g of x, would be divergent as well. And we can actually use this for this exact question right here. But then you're going to ask me, where are we going to get g of x from? They just gave us this function. Well, we can sort of guess that it's going to be a convergent, that this would be a convergent, and we can try to guess a function of what g of x will equal to. Now remember, sine squared x over the root of x has to be smaller than or equal to g of x. So let's call f of x as sine squared of x over the root of x. And let's say g of x. Well, let's get rid of the sine squared, and we'll say 1 over root of x. Now, we can see here that integrating this, a lot easier than computing sine squared x over root of x. So let's integrate the function with these bounds. So we keep the bounds the same, nothing changes, of pi. Well, I forgot one thing. So it's just like the last question. T is equal to 0. So we'll focus on this guy from the right side. Now we do look at the right side because it's in the lower bound. So if, let's say, I had a graph and it looked like this, and this is my lower bound and this is my upper bound, I would want to look at everything from this side. Therefore, we look at the right side. Therefore, we can say that we take the limit as t approaches 0 from the right side of the integral of 1 over root of x from our lovely t to pi of dx. So computing this would be, that becomes x 1 over 2 dx. So I believe that should give you, if you solve this, you should come up with 2 pi of x. The boundaries of pi and t. Hold on, let me check. Yeah. Okay, yeah. So this is what you should be getting. Therefore, you are going to compute the limit as t approaches 0 from the right side of 2 of t, so 2 root pi minus 2 root of t. Now, plug in 0 here, you're going to get 0. because root of 0 is 0 and 2 times 0 is 0. And this is just a constant. So then we end up with that the limit is equal to 2 root of pi. And we can just leave it like that. Therefore, we now have a constant. And with this constant, we can say that our function, so that g of x is convergent to 2 root pi. Now, what does, I'll erase this to make some space. What does that mean? We computed g of x and not f of x. But remember, going back to the comparison theorem test, where we literally have f of x is less than or equal to g of x. So because g of x is convergent to 2 root of 2 root pi, we can tell that this one is also convergent. So f of x is also convergent to 2 root pi. Therefore, right here. Therefore, already in green actually. Therefore, the integral of sine squared of x of x with bounds of 0 to pi of dx is convergent to 2 root pi. Let's go on and do another question, shall we? All right. All right. So we've done this question. All right. So here's another question that is a bonus for you guys, and you you can leave your answers in the comment section below. I'm not gonna solve it, but you guys can leave it in the bottom section below. I'm not gonna solve it right now. I'll solve it in my next video, but where I'll be covering partial fractions decomposition. Yeah, so you guys can take a look at. I'll solve it in the beginning of that video, in the end of the video. Sorry, and so just try to answer this on your own. So what is 1 over? What is the integral of 1 over 3x plus 1 squared dx with the bounds of infinity to 1? I will give you a hint. This is going to be a lovely hint. Oh, it's a type 1. Yeah. So for this question, you need to determine if this function is convergent or divergent. And if it's convergent, compute to where it's convergent. So it's convergent to what value? Alright, good luck and thank you for watching and have a lovely day.